Lesson 9.3, graphing reciprocal functions. So you guys know reciprocal is like 1 over, like 1 over x would look like this right here. Here, I'll pull this up on Desmos, graph this right here. If I say y equals 1 over x, right? So this might be a parent function to a number of functions in this lesson. Right? So, you're not allowed to divide by 0. So if you plug in 0 for x, well, you get that vertical asymptote. All right, so other interesting properties here. I do see a horizontal asymptote at y equals 0. That's if you let x become very, very big. Suppose x was like a million, 1 over a million. Well, the chance of winning, say, the lottery, 1 over a million, that's approximately 0. Okay, so it's asymptotically approaching 0 to the right. If you go to the left, say if you plug in negative a million for x, well, it's negative, but otherwise it's the same story. It also asymptotically approaches 0. You could, of course, make a table. You could plug in various values of x. So plug in x could be 1, 2, 3, 4, 5. You get 1 over 2, or sorry, 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. Right? You can plot as many points as you like. It makes that curve. All right, there you go. So there's real basic parent function. Let's jump into some examples here. Example 1, limitations on domains of reciprocal functions. All right, so remember, if you look for a domain restriction, you're not allowed to divide by 0, right? And then in other parts in this book, maybe you're not allowed to take the square root of a negative, but for this section, it'll say you're not allowed to divide by 0. All right, so we got g of x equals 6 over x. Well, if they're just looking for a domain restriction, I would say that denominator is not allowed to be 0. Yeah, and this graph would look very similar to this. All I have to do is replace this one with a 6. Let's do that. Put a 6 up here. There you go. It just multiplies everything vertically by a factor of 6. Right, so the 0.16 is right here. Right? Okay. The 0.23 is right here. There we go. So that's all right, right? That's all right. Okay, so if I were to properly write out the domain, maybe I could write it like this. So I could say uh, x such that um, x is less than 0, but strictly less than 0. Okay? And then put union x is strictly greater than 0. Okay, so there's your set builder. Okay, or so that's set builder notation. And then there was interval notation. Okay, so again, also domain, I would say parenthesis, negative infinity, comma 0, close parenthesis, then union, open parenthesis, 0, infinity. Okay. These parentheses mean you're not allowed to include 0 itself, right? And then as part of a rule, when you go to infinity or negative infinity, I always put parentheses there. Okay, so that's all right. How about, well, this example right here? Let's jump down to g of x is equal to negative 5 over 3x plus 4. Okay, so getting a bit more interesting here. Uh, I would say 3x plus 4 is not allowed to equal 0. All right, we can do a little algebra. So 3x is not allowed to equal, subtract over 4 to get negative 4. So x is not allowed to equal negative 4 thirds. And so if I'm starting to graph this, I would definitely put a vertical asymptote there. All right, let's go x-axis, y-axis. Okay. Now, if this is, say, -2, -1, 0, 1, 2, okay. 4 thirds is like 1.333, and this is negative. So probably right about here-ish. Going to create a vertical asymptote. Okay. I can always create a table of values and plug in as many values of x as I want. Okay. Here, I'll do a few. So what happens when x is 0? Let's try 2, and let's try about -4. Let's get some points on the board, and then we'll flip over to Desmos and see if it's lining up. It should be good. So if I plug in 0 for x right here, this comes out to 0 plus 4 is 4, -3, -5 over 4, -5 over 4, which is, see, -1, -2, -5 over 4, and 5 fourths is right about here. Got that right? Okay, how about when x is 2? 3 times 2 is 6, plus 4 is 10. Negative 5 over 10 reduces to negative 1 half. Okay, so x is 2, negative 1 half. It's right out here. Let's go to negative 4. So 3 times negative 4 is negative 12, plus 4 is negative 8, and then negative 5 over negative 8 is positive 5/8 or 0.65 if you like. Okay, so I plug in 3, negative 4 way back here. I get positive. Okay, so that's a little more than a half. That's probably right back here. All right, you know what else I should be looking for? How about a horizontal asymptote? Okay. Like, what if you let x get really big, like a million? Well, you have negative 5 over like 3 million, and so, roughly. It's getting really close to zero. And if you let x go to negative a million, this is negative 5 over negative 3 million and something. Okay. So it's asymptotically approaching zero. Let me show you guys a different way. Here, I'm going to write this in pinky because your book doesn't exactly say spell it out this way. But to find the horizontal asymptote, okay, you can divide every one of these three terms. You can think of this way, like that's a term, that's a term, that's a term by x, and it will look like this. G of x equals negative 5 over x over, now 3x over x is just 3. And then we got plus 4 over x. Like that. And then, all right, and I'm going to jump ahead in math and use some notation you may not have seen before, maybe, right? Is what if you limit x approaches infinity, right? Is a marker of a horizontal asymptote is if you let x go to infinity or negative infinity for that matter. I'll just let it run to infinity. If you do that, what's negative 5 over infinity? Well, that would become 0. And 4 over infinity, also 0. Like 4 in a million is like 0. Okay. So you have 0 over 3 plus 0, 0 over 3, which just goes to 0. Okay. Now notice I'm saying limit as x approaches that value. Okay, so it'll never actually reach this value, but we can get this horizontal asymptote properly on the board. So look like this. So put it all together. I think what this graph is really going to look like here. Let's do some ballooning. It's kind of standing out. Okay. It should go like this. Should go like this, and then I bet this goes roughly like that. Okay. But that looks pretty close to what it looks like. Okay, so we're looking at this right here. And I'm going to pull this up on Desmos. Negative 5 over 3x plus 4. Let's do that. Put a negative 5 on top. Come on here. And 3x plus 4 down here. 3x plus 4. Right. Yeah, that is it. That's exactly the way it is graphed. Same thing. All right. Yeah, pretty good. Pretty good. All right, that is that. All right. We got next example here. Graph the reciprocal function by, using a table. Okay, well, actually, I was kind of setting up a table with you guys right here. Okay, so that's been a method we've been using over and over in this class. You can always just plot a bunch of points and see what emerges. Could be helpful. That's fine. Okay, so let's go. G of x is 1 over 2x minus 5, and the whole thing plus 2. Okay. Well, I still want to figure out where the asymptotes are. So let me go ahead and do that. So I'll say vertical asymptote where 2x minus 5 is equal to 0, because then you would be dividing by 0. So 2x would be 5, or x would be 5 over 2, which is 2.5. Okay? So that's going to be my vertical asymptote. Say horizontal asymptote. Let's say if you let x go to, say, a million, then this is like 1 over 2 million roughly, right? Which is approaching 0. And you get plus 2, right? Now if you let x go to negative a million, right? So I'll say limit x goes to infinity, or limit x goes to negative infinity. Either way, this fraction goes to 0. You could also divide each of these three pieces by x and do this trick I did over here in pinky just a couple minutes ago. Okay? You would still get that. Right, so this plus 2 is going to dominate when x goes to infinity or negative infinity. So g of x approaches 2. Right, so you say y equals 2 would be the horizontal asymptote. Right, so You gotta get a graph going. Now your book is trying to encourage you to use a table here, so you got a table of values too. Let's get some axes, x, y. I know there's something special happening that x is 2.5. That's the vertical asymptote. So let's go 1, 2, 3, 4, 2, 3, 4. All right, see where this gets us. Let's create an XY table here. Here we go. Switch ink color. X, Y to make this table. Okay. So let's go about 0, 1, 2, 3, 4. Let's run those numbers and see what happens. Okay. Right now, here, I'm going to use this calculator trick. Here's the trick I've done with you guys in the past. If I do 1 over and then put this in parentheses, yeah, I'll go ahead and put this in parentheses. Okay. 2 answer minus 5. So the calculator can treat answer sort of like x, and I can very quickly pop in new numbers there. I'm going to close that and say plus 2. Right. And then I'll start plugging values. So if I plug in 0, okay, now the calculator's thinking, okay, 0, something about 0. You scroll up, plug 0 into this expression, and it'll tell you exactly. It says 1.8. 1, scroll up, plug in. You got 1.67. I'm rounding a little bit. 2, I get 1 exactly. 3, I get 3. 4, I get 2.33. Right. And I could go on, I can make a table as big as you want, but let's plot these points and see if anything's emerging out of this. Okay. And so I know vertical asymptote at x is 2.5. I'll go ahead and throw that on the board. I said, okay, so there's your vertical asymptote. X is 2.5. Here's your horizontal asymptote. It's like y equals 2, or this whole thing's going to eventually approach 2. Okay. This is kind of divides my graph into these different regions. Okay. And let's plot these 5 points, see what happens. 0, 1.8. Let's write that here. 1, 1.67. Back here. 2, 1. 3, 3. So right here. 4, 2.33. Yeah, I think I see what's happening. Right. I bet when I go to Desmos and type this equation in, or if I extended my table and added on more and more and more points, it would eventually create this looking shape right here. But that's exactly it. Right, you guys think? I bet that's going to be the answer. Right, so right here, go to Desmos, type this in, and see if that's what comes out. Okay, so Desmos. All right, so I'm going to copy this right here. So I got 1 over, let's see, 2x, and then minus 5, and the whole thing plus 2, right, which would shift up to. Let's see, is Desmos graph, my graph, the same thing? There's my graph. There's Desmos graph. Yeah, that's the same thing. That's exactly the same thing. Whoop. Where'd the graph go? Or, okay, wow. And then zoom around a little bit. Yeah, that's the same thing. All right. All right, so we're doing good. Doing good. Um, let's do example 3. Analyze a reciprocal function. Oh, Ohm's law. All right, so we got a physics example going on here. We've got electric circuits operate according to this equation. So we got example 3. They're telling you I equals V over R, where I is the electrical current. Electrical current. Because the letter C is used for so many other things, so run out of letters. I guess they're using I for current. And it's the same thing in my class. We always teach that. V is the voltage, also called electric potential, and R is the resistance. Okay. So if you have, say, a AA battery, guys, a AA battery is like 1.5 volts. Right? If you plug that in to, say, some light bulb you hook it to has some amount of resistance in the filament, there's going to be some current in amps that ends up flowing. Okay? Or if you have two AA batteries and you stack them on top of each other, you can get 3 volts. And then on some light bulb produces like some current in amps that's flowing. And that's the basic story. And we got here committed force in volts, R is resistance in ohms. Analyze the electric current of a 110 volt curling iron in relation to its resistance of its circuit. So they're telling you V is 110. That's volts, right? Um, okay, so I guess it's like this. Right? So I equals 110 volts over R. Okay? All the outlets in this room are about 120 volts alternating current. Right? So when you plug an appliance into them, then you get some current and amps to flow. Right? I think some countries in Central America they use more like 110 volts, something like that, but roughly. Okay. All right. So what can I do with this? All right. So well, really, you only have positive resistances. I don't think there's such a thing as a negative resistance, right? Unless something I'm not aware of. Okay? Let's put resistance in ohms on this axis. Let's put current in amps on this axis. Okay? It will come up with a table. Actually, this would be a good space for a table because I think this negative part of the graph would be irrelevant. Anyway, it's come with different resistances and ohms, and what's the resulting current in amps. Okay. So let's go resistance. How about 1, 10, 110. Let's try that. Okay. Because if you take 110 divided by 1, you get 110. That's 110 amps. If you had 10 ohms here, 110 over 10 would be 11 amps. If you had 110 ohms here, 110 over 110 is 1, as in 1 amp. Okay? So let's go to resistance. Put 10 about here, 1 about here, 110 about here. I don't know if that's exactly the scale, but you guys get the idea. Okay. And the same thing this way. 1, 10, 110, something like that. Okay, so the point's going to go 1 comma 110. Whoops, 10, 10, 11 it is. 11, I guess 10, 11, and 11, 10. 10, 11, 11, 10 be each a pair of points. Okay. And then 1, 10, 1, like that. Right. So getting a graph that looks like this pretty much. Okay. So given some voltage source, like the wall outlet, right? If you plug something into a wall outlet, and let's say it's giving you 110 volts alternating current, the more resistance you have in your electrical appliance, the less current in amps that ends up flowing. Yeah, that's an inverse relationship. Okay. You wouldn't want to have zero resistance. That's like, here, okay, you guys know not to just plug bare metal into the outlets, right? Like if you go jamming a fork into the outlet, you're gonna get shocked and possibly die, right? Right, because there'd be zero resistance. There could be just current that flows like with with no resistance, right? So we're hitting that Burke Blossom tip there. That would be bad. You don't want the current flowing through you. Right? It's just near infinite amount of current. So don't go jamming forks into outlets. Yeah. All right, let's do, cabin rental. That sounds fun. A group of friends plans to rent a cabin at Red Pine Ski Lodge. The cabin costs $750 to rent for the weekend. And what I'm thinking is that's probably regardless of how many friends show up. If one guy shows up, it's $750. If 10 friends show up, it's still $750. But now, hey, now they can divvy the price among all their friends. Yeah. Let X be the number of friends sharing the cost. Y be the cost per person. Oh, yeah, that's exactly where you're going with this. Yeah, so yeah. All right, so call this cabin rental. All right. So let's say Y, which is cost per person. Okay. Well, we're going to take $750 and divide by X, where X is um, number of friends sharing the cabin, right? So again, if here, make a little table to back up what I'm saying here. Okay? So yeah, X friends and Y cost. Okay? So what if one guy shows up? I guess he's his only friend. Or what if two friends show up? Right, like a duo. All right, what if three friends show up? Let's go with 5 friends, 10 friends. What would be the cost of this? So if one guy shows up, he has to pay the cost all himself, $750. But 2 friends, well, now you get 750 over 2. They each pitch in $375, and now they got the cabin. Hey, what about 3 friends? That's $250 each. How about five friends? $150 each, and then 10 friends be $75 each. All right. So I think this will be similar to the electricity story in the case that you can only have a positive number of friends. So let's just work with the positive values of x. Yeah. Okay, and then put y cost right here. Okay. Let's go 1, 2, 3, 4, 5 friends, 6, 7, 8, 9, 10 friends right here. Okay. And then let's go 100, 200, 300, 400, 500. Wow. And we kind of messed that up. Cut that in half. Okay, let's do this. Okay. So go 100, 200, $300, $400, $500, $600, $700, $800. Okay. So one guy shows up, 750, 750, that's right there. Two, 375, three, 250, five, 150, 10, 75, like that. Right. Yeah, this is looking pretty well in line with all the graphs we've been making so far. Right, something like this. Right. Really, I guess you have a discrete number of friends, right? But yeah, it follows that curve like that. All right, and then yeah, that's the function. Right. So if I pop that into Desmos, it would look like that. Yeah. All right. Ooh, transformations. Got example four, transformation of a function. So if you just focus on this blue graph right here, this looks like y equals 1 over x. Yeah, it says y equals 1 over x. All right, now how can we shift this around to get this pink looking curve called g of x? Well, okay, I see a couple of asymptotes. Okay, here, let's follow this model right here. Maybe we should start with that model. All right, we got I'll call this transformations. All right, and we'll get g of x based on f of x. Okay. So we have some vertical stretch factor over x minus h and the whole thing plus k. So a refers to vertical stretch. H is the horizontal shift. And notice they're subtracting it off. So if you subtract something, you're going to the right h units. If it said plus h down here, you'd be going to the left. So remember, horizontal minuses to the right and pluses to the left. It's always been like that in this class. And probably you go back to Algebra 1. I think you guys probably did some of this too. This plus k is a vertical shift. Right? It'll just shift the whole thing up k units. Or if it said minus k, it'd be down k units. Okay? All right, so using this as a model, how can we make sense of this? All right, so it looks like f of x is just plain 1 over x, so that's nice. Okay. And then I see this vertical asymptote. It looks like it shifted to the left 1 unit. So I'm going to say this h right here could be plus 1, or well, it'd be x plus 1 down here. I guess h would be -1, so you're subtracting a negative. It's going to the left. Okay. And I also see the horizontal asymptote is like down 2. So let's go g of x equals, and I'm going to leave a space for a. I'll come back to that vertical stretch later. But right away, I see what's going on with the asymptotes. So I'm going to say x plus 1 here because of the left 1. Right, that's what made me say plus 1. Okay. I'm going to say minus 2 on the end because it was down 2. Again, just following those asymptotes, going from the pair of blue curves to the pair of red looking curves. Right. There's one more detail I want to get in place, which is there a vertical stretch here? And for that, I'm going to pick a point like 1, 1 on the original blue graph. Let's see, if I go left 1 down 2, left 1 down 2. Okay, so yep, everything's pairing up so far. That's fine. Okay. But then what about, say, a point like, say, 1/2, comma 2? Now, if that also lines up, then I think this a could just be 1. But if it doesn't, I don't know how much to stretch it. Let's see. Okay, so go so left 1 down 2, left 1 down 2. You know what? That is lining up exactly. Okay. I think this red graph and this blue graph are stretched exactly the same. Like you could just shift them right on top of each other. So I think this A is just one right here. Okay. So like if it was like stretched by a factor of three or something vertically, then I have to put a three up there. But I think this is the whole thing, right, for going from this blue to this red. Yeah, should be it. All right. Oh, here they're talking about domain and range. Let's set that. Okay, so domain, I'll do x such that uh, x is less than -1, right? Or x is greater than -1, right? X is not allowed to equal -1 because then you'd be divided by zero. Okay? So there's your set builder. I think before I put a union here and I'm saying or, okay, that's another way to say that. All right, then range. Well, the range of this g of x would be everything except for the horizontal asymptote, right? So I don't think there's any way to ever make this y equal to exactly -2. Because like you could plug in a million for x and you get 1/1,000,000 plus 1, which is almost zero, but not quite zero, and then -2. This fraction will never be zero. So, and you can see that too in the graph. I mean, I created this equation from this graph. -2, the y value will never be equal to. So let's go y such that y is less than -2 or y greater than -2, but it can't equal -2. The range can't. Okay. I have let's talk about asymptotes. Got a vertical asymptote at mm, x equals -1. Because again, if you plug in -1 here, you would be divided by zero. Can't do that. That aligns with the graph. There's a horizontal asymptote at, let's see, horizontal uh, y equals -2. Yeah, like that. All right, so I think that's about it. All right, so okay, so now we got transformations. Right, got possible shifts or stretches rather. Okay, horizontal shift, vertical shift. All right, let's do one more of these examples, then we'll jump into the book questions. All right, example 5, write a reciprocal function from the graph. Okay, so it's, yep, pretty much what we just did. Just another example. Okay, so example 5. So the model is g of x equals a over x minus h, and the whole thing plus k. Again, vertical stretch, horizontal shift, vertical shift. Got it all right here. Okay, going from this red to this blue. Looks like my f of x is very simply 1 over x. Okay, so it's again like a parent function. Okay, now g of x relative to that, let's see, let's check the asymptotes first. So it looks like the vertical asymptote's been shifted to the left 4. You guys see the left 4? So I'll say g of x equals, okay, I'm going to come back to the stretch factor, just that later, okay? But left 4, that would give me x plus 4 down here, or x minus -4 if you like. Let's call it x plus 4. That's left 4. Left 4, because I'm just following that vertical asymptote. Now the horizontal asymptote looks like it went down 2. So I'll say -2 is going to be tagged to the end. Because the whole thing down 2. Okay. Now the last detail I need is what is this vertical stretch factor right here? Okay. So they gave us a point on the graph. They gave us -3, 3. Okay. Now one way to handle that is just plug in that coordinate and just solve for a. So I'm going to do that. I'm going to say, let's solve it down here. 3, the y value of 3, is equal to, okay, now I'm going to solve for a, but this y value 3 shows up when you plug in -3 for x. Okay, they got +4 here and -2 here. All right, so let's just go solve for a, and then we'll have the answer. So this right here, I'll go ahead and box it in, okay, because as soon as we get this a value, then that will eventually be the answer. Right, so let's add 2 to both sides. Do +2 plus 2. That gives me 5 is equal to a over, you know what, I can consolidate this too, because this is just 1. Oh, actually, that's it, isn't it? A is 5. A is 5. So go up here, put 5, and now we got the answer. Okay, so it's like that. All right. Um, see, does the graph kind of look like that? Well, okay. If you were to take this blue graph, shift it left 4 down 2, and then stretch it vertically by a factor of 5, then one of the points would be negative 3, 3. All right. Boom. Let's jump into the text questions. Somebody's highlighted. Identify asymptotes, domain, range, graph the function, key features. Yeah, let's do all of that. So number nine here. I got f of x equals 5 over x plus 4. Right. So I know there's a domain restriction where x cannot be negative 4. So domain, okay, I can say x such that x is less than negative 4 or x greater than negative 4. That's your set builder notation. Or just simply x cannot equal negative 4. Maybe that's an even more efficient way to say that. Okay. And the range, uh, okay, let me do this weird trick I did before. Okay. I'll switch sheet color here. Okay. So I'm gonna take all three of these terms, the 5, the x, and the 4, and divide them each by x. I'm gonna show you guys a trick from, well, future math, I guess. It might have introduced this in math class. I'm gonna say limit x goes to infinity. Okay? Because, and you could also go negative infinity, but I think it'll be the same horizontal asymptote either way on this one. Okay. So if you do that, what is 4 over infinity? It's, well, like 4 over a million, 4 over a billion. Okay. Like what's the chance of winning a lottery winning the lottery if you buy 4 tickets? Approximately 0. So this goes to 0. Same thing with 5 over x, this goes to 0. Okay. And this x over x would go to 1. Right? So the whole thing becomes 0 over 1 plus 0, just goes to 0. Okay? So what this means, stay in peaking since that's what it was just shown here, okay, is that there's a horizontal asymptote at x equals 0. Okay? Or to go back and fill it in, the range could be y such that y is strictly less than 0, or y is strictly greater than 0. Okay. Great. This is going to look like, okay. So I have a domain, range, got some asymptotes I'm looking for. Oops, I need to spell out vertical asymptote at x equals negative 4. Okay, have that too. Okay. So let's put x here, y here, 2, 3, 4. Here's negative 4. X is negative 4. Okay. So I know there's going to be a vertical asymptote right here. Okay. Let's get a bunch of points. So pick a table, x, y table. Well, I'd like to know what's going on both sides of the negative 4. So let's go um, about negative 10, negative 5. Let's go negative 3, 0. Um, how about 6? All right. I bet that'll be enough where the graph is going to emerge. Okay. All right, so here's the function right here. I'll do that calculator trick I did earlier. I'll do 5 over, and then in parentheses, I'll put answer plus 4. Okay. Remember, I just put this right here in parentheses. Okay. All right, then I can start plugging the values. Negative 10. Then scroll up, put that in, and it's telling me negative 0.83 something. Negative 5. I'm getting negative 5. Negative 3. I'm getting positive 5. 0. I'm getting 1.25. And 6. I'm getting 0.5. All right, so let's plot those points. Well, I did put the vertical asymptote there. May as well put the horizontal also. I mean, there will be a horizontal asymptote here. Okay. All right, so let's see, negative 4, negative 5, 6, 7, 8, 9, 10. So negative 10 is way back here. Negative 0 point something. say 2, 3, 4, 5, -5, 2, 3, 4, 5, 2, 3, 4, 5, 6. Okay. So -10, -0.83, it's like right about here. -5, -5 is right here. -3, +5, notice it jumps way up here. 0, 1.25, 6.5. Right? Yeah, we can graph all of. Very nice looking graph. Yep, that's about what I was thinking. Yeah, yeah, I'm seeing that vertical asymptote exactly where I thought. Okay. On either side of the vertical asymptote jumps wildly, negative versus positive. Okay. Got this horizontal asymptote where these y values are approaching zero, both to the left and to the right. Yeah, that's it. All right, one more down. Uh, Number 10. F of x is 6 over x, and the whole thing minus 3. Okay. So this kind of reminds me of transformations, right? Like if you took 1 over x as a parent function, you could stretch it vertically by a factor of 6, then shift the whole thing down 3, like that. Right? Or let's get a table of values and plot some points, x, y. Okay. Now I know x is not allowed to equal 0. Let's go uh, -3, -2, -1, 0, 1, 2, 3. So if I plug in -3, we don't even need to calculate for this. 6 divided by -3 is -2. Minus 3 is -5. 6 over -2 is -3. Minus 3 is -6. 6 over -1 is -6. Minus 3 is -9. 6 over 0 does not exist. There's your vertical asymptote. 6 over 1 is 6. Minus 3 is 3. 6 over 2 is 3 minus 3 is 0. 6 over 3 is 2. Minus 3 is -1. Okay. Interesting set of points. All right. So I went from -3 to 3 on the x-axis. But my y-axis goes to -9. Yeah. Okay, so this is going to be skewed a little bit, but they'll create the basic correct shape. Let's go -3, -6, -9. Let's do that. Right. So you guys do see I have a scrunched y-axis, but that's okay. We'll be able to work with that. Okay. So -3, -5 is right here. -2, -6 right here. -1, -9. 0 vertical asymptote. Ooh, vertical asymptote. Right. While I'm drawing asymptotes, maybe I should have done this to start with. Do you see what the horizontal asymptote is going to be? If I divide by like a million, this will approach 0, or -1,000,000 for that matter. This will approach 0, then -3. There's definitely going to be a horizontal asymptote down here at -3. Okay. All right, so let's keep plotting these points. 1, comma 3. Ooh, that's here. Notice this jumped from way down here, way up here, because we just crossed the vertical asymptote. 2, 0, 3, -1. Okay. Put it all together, looking like that, like that. Yeah, that's it. There's your graph. All right, number 11, planes. A plane is scheduled to leave Dallas for an 800-mile flight to Chicago's O'Hare Airport. However, the departure is delayed for 2 hours. Let t equals 0 represent the scheduled departure time. Write a function that represents the plane's average speed on the vertical axis as a function of travel time, which is based on the travel from the scheduled departure time to the destination. Graph the function. All right, so uh, okay, I know that speed is distance over time. Okay, so I think we're gonna use that as the framework to set up an equation. Okay. And they want average speed, they're calling R. Okay, so this R equals, now the flight is 800 miles. So let's put 800 miles right here. Okay. But what about the time? Now it says it's delayed for 2 hours, delayed for 2 hours. Okay. Um, okay. So here's where I think you gotta apply some interpretation. It says let's go T based on the travel from the scheduled departure time to the destination. Uh, the way I'm going to interpret this is what's the average speed like after the plane is taken off, but we're doing times relative to the departure time. Okay, and we lost 2 hours. So here I'm going to interpret it this way. Say T minus two, and this two represents the 2 hour delay. Right. Here's why I think I would interpret it this way. Okay, because let's say 2 hours have elapsed. Okay, we've got a 2 hour delay. Right, so now suppose it was supposed to leave at 12 o'clock, but it actually leaves at 2 o'clock. Okay, so we got 2 hour delay. Okay, now if the plane instantaneously just teleported to Chicago, okay, then you could interpret that as infinite speed or like the speed of light. You'd be basically dividing by zero. Okay, uh, if it took the plane 1 hour of flight to reach Chicago, okay, then that would be 3 hours after the departure time. So you say 3 hours after the departure minus the 2 hour delay. It's only been in the air for a single hour. And so it's going 800 miles per hour on average. So yeah, I think that's what I'm going to go with. I checked the teacher's manual too, and they have that equation. So I think they're going with the same interpretation that I am. So we'll go with that. I don't know. What could this look like? Let's see. Let's look like. So let's put time here. Let's put, I guess, R for rate, maybe, or speed. Anyway, this is miles per hour here. And this could be in hours here. Okay. So maybe we could take some number of hours. Let's go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Now keep in mind, this is the time after the scheduled departure time. Okay. So during the first 2 hours, the plane's just sitting there doing nothing. Okay. And if it at the 2 hour mark suddenly teleported to Chicago, well, that'd be like infinite speed. So we'll treat that as the vertical asymptote right there. Also, if you do minus two on the x variable, which in this case t, it's going to shift the whole graph to the right, which is exactly what this looks like. Yeah. All right. Let's get some values. Create a TR table. So hours, miles per hour. Okay. What if the plane got there after hour number three, like 3 o'clock after noon? Okay. Or 4 hours later, or 5 hours later. Okay, let's do this. Okay. So if I plug in 800 over 3 minus 2, that gives me 800 miles per hour. If I plug in a 4 right here, I get 400 miles per hour. And a 5, I get 267 miles per hour. Okay, so let's go 500, 1,000. Okay. So at 3 hours, it'd be 800. That's right about here. 400, 267. Right about there. Yeah. I'm getting a graph that looks like this. There we go. Okay. Think that's what they've been looking for. All right, number 12, computers. To manufacture a specific model of computer, a company pays 5,000 to rent and overhead and 435 per computer for parts. Create a function relating average cost of a computer C to how many computers N were made and graph the function. Okay. So uh, here, write down the key facts here. $5,000 for rent. Okay. And that's a fixed cost. I'll put that fixed cost. If they make one computer or 1,000 computers, then it's still $5,000 to rent regardless. Okay. They also say 435 per computer. Okay. N equals number of computers. they manufacture, or wait, pays, or what are they buy, oh yeah, manufactured. Okay, and C, their, what is that average cost? Yeah, average cost. Average cost per computer. Okay. Average cost, that sounds like the total dollars divided by the total number of computers. So let's see if I can set that up, see where this goes. So average cost would be the total cost, which would be $435 per computer times the number of computers, right? Because it costs them $435 every time to make a computer times the number of computers, okay? Plus this $5,000 rent, regardless of the number of computers they make, right? And so that's the total cost, and then divided by the number of computers. So total cost divided by number of computers results in average cost. Yeah. Okay, so I think that's what we're looking for right there. Right. Now, there's another way, yeah, you could write this. Like this is perfectly valid. Another way you could think of this is that the cost is equal to, okay, you could divide this out because really simple denominator. This could be $435 per computer plus that $5,000 rent divided by the number of computers. This and this are the same equation. So I'll say those are the same. Those are the same. Yeah, same thing. Okay. Hey, you know what? Here, I'll do this one in Desmos. That'll be a little bit different. Just to show you guys that these are, in fact, the same. Here, graph these one at a time here. All right, so let's clear all this up. I think Desmos should understand C and N. Let's see if it does. So let's go 435 N plus 5,000. All right, and then collectively divide that by N. Let's see. It's going to be able to help with that. Now, yeah, okay. Yeah, and notice this too, is that if you only manufacture a couple of computers, the average cost is going to be really high because you had to pay all that rent. But if you manufacture like thousands of computers, then that rent gets divided by thousands of computers. So the average cost is going to asymptotically approach 435. And you can see that horizontal asymptote right here at 435. Okay. Now, here, what if I type this other equation, which I'm saying is the same thing. So it should overlay exactly on top of it. C equals 435 plus, and then 5,000 over n. It should be exactly the same. Let's see. Yeah, right. Notice that blue curve lies right on top of the red curve. That's why you can't see the red anymore. But okay, it's exactly the same thing. Yeah, pretty good. Pretty good. Right there. All right, let's do some transformations here. Transformations. Uh, let's at least do this one, number 20. Ooh, this looks exciting here. There, pull this up closer to the screen. So it looks like this blue function, f of x is the parent function, which is just simply 1 over x. So f of x is 1 over x. I'll go ahead and write that down. F of x is very simply 1 over x. Okay. Now, how do you get this g of x, red looking function? It looks like, let's look at the asymptotes where it is shift. It looks like it shifted left 3. Uh, um, right. Oh, and I think it has the same horizontal asymptote as before, so it didn't shift up or down, but it was stretched vertically because look, it goes to the point 5, 1. So let's do that. Okay, so I'm going to say g of x is f of x left 3 and also stretched. So it goes through, they gave us a point 5, comma 1. So let's try that. Okay. So I'll say g of x is, there's some vertical stretch factor A that we're going to have to solve for. I don't know what it is yet, but we're going to find. Okay. And then left 3, that like x plus 3 goes right here. Okay. All right, now let's take advantage of this coordinate 5, 1 to solve for A. So when x is 5, we got plus 3, got an A here, we're solving for. I know g of x is 1. Okay, so here's your coordinate 5, 1 right here. Okay. X, Y, 5, 1. Okay. So see 5 and 3 is 8. Cross multiply that. 8 is equal to A. Okay. Now we know that A is 8, is 5 plus 3, cross multiply. Okay. We can get the full g of x, which is 8 divided by x plus 3. Okay. One last check. Let me make sure that this 0.51 works. So if you plug in 5 for x, 5 plus 3 is 8, 8 over 8 is 1. Yeah, that's it. So yeah, we've got a vertical stretch of 8. Vertical stretch of 8. Okay, so that. All right, and let's do a couple more here. Number 38. 38. Got f of x equals 2 over x plus, or minus 4, x minus 4, and then the whole thing plus 3. Okay. All right, so what do they want? Domain, range, asymptotes. Okay, so I think domain, uh, x such that x is less than 4, strictly less than 4, or x is strictly greater than 4. Okay. But x cannot be 4 because then you would be dividing by 0. Remember, not allowed to divide by 0. Okay. The range. Okay. Um, well, let's think what would happen if x goes to either infinity or negative infinity. This denominator would blow up big, and 2 over something would approach 0 but never quite be 0. Right? This fraction can never exactly be 0, but it will approach it if x gets very, very big, positive or negative. Okay? So something not quite 0. Plus is 3. I think that y is allowed to be strictly less than 3 or strictly greater than 3, but y will never be 3. Okay? And this brings me to asymptotes. So the horizontal asymptote, well, actually, that's what I just did here, okay, is that y is 3. And the vertical asymptote, okay, so actually this one goes with this one goes with this one. Vertical asymptote would be at x equals 4, because remember, that's what it's not allowed to equal. Right. All right, so let's frame a graph around those asymptotes and then create a table of values and see what happens. Right, so y is 3, 1, 2, 3, right here. X is 4, 1, 2, 3, 4, it's right here. All right, so I'm looking for there to be an asymptote right here, an asymptote right here. Right. Okay, so I wonder if my graph's gonna look something kind of like this, right? A lot of them have been looking kind of like that. Right? Come up with an XY table, X, Y. Okay. And I want to know what's going on either side of 4. So let's go 0, uh, 1, 2, okay, and then let's go about 5, 6, see what happens. Okay, so I'll throw in 7 and see what happens. So let's go 2 divided by answer minus 4, and then the whole thing plus 3. Okay. And then I need to come up with some values. So let's start with 0. All right, plug in 0 to this expression, you get 2.5. Plug in 1, I get 2.33. Plug in 2, I get 2. Plug in 5, I get 5. Plug in 6, I get 4. Plug in 7, I get 3.67. Okay. That should be enough points to tell the story. All right, so let's plug this in. 5, 6, 7, 4, 5, 6. All right, so you got 0, comma 2.5, 1, comma 2.33, 2, 2. Kind of curious. I should have thrown in 3. Well, let me see what happens with 3. 3, I get 1. 3, 1. That's a point. Okay. But let me show you guys. What if I plug in 3.9? 3.9. That's getting really close to the asymptote, right? I bet it'll be negative. Let's see if it is. It is, yeah, it's like negative 17. So that's like way down here at like right down here. We got these other points. 5, 5 is a point. Oh, hey, it jumps way up here because when we cross the vertical asymptote. 6, 4, 7, 3.67. Yeah, yeah, we're definitely getting the full story right here. It's gonna go down like that, like that. It's gonna go like this. Yep, everything's lining up. Looks good. Looks good. Yeah. Oh, and that's okay. There's the equation that we've been graphing. So it's that right there. That's that. All right. All right, one more. Number 46, money. Some students are renting a bus for a trip to an aquarium. The bus costs $200. Aquarium tickets are $25 per person. Let's have the total cost per student is Y. There are X students and they share the cost of the bus equally. What's the cost per student? That's a 46. So bus cost equals $200. Okay. Ticket, aquarium ticket, also called AQ ticket, is $25, oops, per person. Right. Right. So if one student buys a bus for himself, then he has to pay the full $200. If like 10 students buy the bus, they get to split the cost of the bus. Now it's only $20 per student for the bus. Right. Right. Now every single student does have to buy a ticket, or maybe we'll be responsible for buying a ticket. So let's say X equals number of students and Y equals cost per student. Right? I think I'll say Y, the cost equals, well, there's a $200 um, bus plus $25 per person for a ticket times the number of students buying tickets, collectively divided by the number of students can give you the cost per person. Okay. So I think this is a perfectly valid formula. There's another way you could also write this. This looks familiar to something we did earlier today. Since that's such a simple denominator, you could very simply divide. You could call this 200 over x, and then plus this would divide out to just 25. Okay. So both of these would be equally valid. These are the same as each other. Same thing. Right, same thing. All right. And see what would this look like? Let's put X students here, Y average cost right here. So this is students. Call this average cost. Okay. I wonder what would be for just one student. Okay. And then let's go 5 students, 10 students, 20 students. I think that should tell the story. Okay. Okay. So let's do 200 over X plus 25. I'm using this version right here. Again, these are the same thing. Okay, so let's plug in 1, get 225. Yeah, if one student goes by himself, he has to buy the bus and his own ticket. He'd be paying 225. There's only one of them, so the average cost is 225. Let's get a group of 5 students. This comes out to $65 per student. 10 students, 20 and 25 makes 45. Yeah. Let's have 20 students. Get $35 per student. Yeah. You see, this is asymptotically going to approach 25, right? Now, you could have like 1,000 students, and the average cost would still be a little more than $25, but the cost per student for the bus would be very small at that point. They still got to each buy the aquarium ticket. Okay, so let's put a asymptote. Oh, okay, well, I could go up to 225. Let's go. Let's go 100, 200. Okay. And I want to fit 25 on here because this is going to be your horizontal asymptote. It doesn't matter if they have like 10,000 students going on the trip. The average cost will never quite match 25. It asymptotically approach that. All right, so let's go 10 students, 20 students, got five, got one. Okay. If it was one student, 225, that's right about here. 565, it's right about here. 1045, 2035. Yeah, that's it. There's your average cost curve right there. All right. Little bus in the aquarium. All right, and that is a wrap on 9-4.